Good afternoon, everyone. My name is Masoomeh Farrokhtar. I'm from Polytechnic University of Milan. The subject that I'm going to present here is the evaluation of the fracture characteristics of metal ceramic composites produced by additive manufacturing. In 2022, it was predicted that 3D printing can achieve a major leap in market share by 2026. As we are now in the middle of this period, it would be beneficial to remind some of the advantages of additive manufacturing, because we see that additive manufacturing is widespread in many aspects nowadays. Of course, I'm just reminding the ones that are related to the current project. Advantages of additive manufacturing are fast prototyping, and the ability to build complex geometries, customization, producing most of the things where they are needed, and also producing the materials with any specified mechanical and geometric characteristics. In the current project, we are talking about 3D printed bioscaffolds. An ideal bioscaffold requires good biocompatibility and moderate mechanical properties. It should have the ability to form complex shapes with high porosity. Ceramic scaffolds are biocompatible. However, ceramic is one of the major drawbacks of ceramic scaffolds is their brittle behavior. So, in order to overcome this limitation, we are going to add metal to ceramic scaffolds. So we are using metal ceramic scaffolds with composite filaments, which have a metal core and a ceramic shell with its biocompatible behavior. Our specimens are going to be produced at University of Padova in Italy. The 3D printing technology that is going to be used is coaxial nozzles, and the ink is based on metal and ceramic powders, which are embedded in visco-epoxy resin that is going to evaporate during the sintering process. At the end of the process, we see that the microstructure of the final material is so porous. The porosity is more than 40%. So it makes us to evaluate the material properties of these microstructures. In the current project, actually, we are using an indirect mechanical characterization, which is mainly based on bending tests. And at the same time, we are comparing our results with the numerical simulations. The specimen that we are going to work on are the pure metal filaments and the ceramic filaments in two different geometry, the core and the shell shapes, and also the composite ones with a metal core and a ceramic shell. And the tests that are going to be used are the 4-point bending test and also the 3-point bending tests. The scaffolds that are also produced are the ceramic ones in two different geometry, and also the composite ones. And the test that is going to be used here is the compression test. In this slide, we are presenting the typical output of the experiments, the 4-point bending test experiments. And as we see on the left, the pure metal results are presented. And we see that they have a ductile behavior, and the tensile strength values are dispersed. On the right, we see the results of the 4-point bending test of ceramic filaments, which are made of alumina, and we see that they are brittle. By using the results of the bending tests that we had, we extracted the material characteristics of metal, and we used it as the input of our simulation by Abacus software. And these data are going to be used to model and simulate the composite scaffolds in advance. In this slide, we are presenting the typical output of the 4-point bending test of the composite filament. And here we see that the first sharp drop, the blue one that we have, is for the first crack, which is the deepest crack in the shell, I mean the ceramic part. And after that, the next one, the yellow or orange one, is the next and the second crack that is going to happen. And we see that the second crack is not going to change the trend of the curve significantly. And there's also another peak at the end of the curve, which is not significant because it's due to the secondary contacts. And another point that we saw on this curve is that after the first crack, when the shell is going to break, the ductile behavior is going to be evidence which shows that the metal core is going to work. In this slide, we are comparing the output of the 4-point bending test of the composite with the simulated pure metal core. And we see that while the cracks are going to happen, the resistance of the composite filament is still more than the pure metal. It means that although the shell is going to break, it is still working and adding strength to the composite filament. According to the experiments, we know in advance that where the crack is going to happen. So to simulate the composite filament, we are going to use a cohesive layer to model the crack. And the characterization of that cohesive layer, which is used, is the traction separation law. And as the tensile strength reaches its maximum value, it starts to progressively reduce, and after reaching the separation value, the element is going to be removed and the crack is going to form. In this slide, one of the most important points in the composite filament is the behavior that the contribution of the core and the shell together are going to add to this specimens. And we wanted to check that if we use a perfect adhesion simulated model and a debonded one, what would happen? And here we were able to capture the first drop by using the debonded model. Although we know that for capturing the next peaks, we need to work on that, but at least we can say that a perfect adhesion model is not going to simulate such models well. And in the further steps, we are going to work on the scaffolds and simulate them, but at first we need to know more about the filaments alone, and then we can use them for scaffolds. And in conclusion, additive manufacturing can produce patient-specific composite scaffolds. The mechanical characteristics and the fracture properties of these components depend on the production process and related details. Simulation models of the experiments can provide an insight on the load transfer mechanisms and support the parameter calibration procedure. The complex fracture patterns observed in the brittle ceramics considered in the present work entail the use of sophisticated computing tools. And thank you for that.